Phillips Laboratories Propulsion Directorate, Edwards Air Force Base, California, providing the United States with space and missile propulsion technology since 1952. Covering more than 65 square miles, it is the largest tenant organization on Edwards Air Force Base, with assets totaling over $1 billion. Once named the Air Force Rocket Propulsion Laboratory, and more recently the Astronautics Laboratory, the personnel and facilities here have developed and provided the technology answers to the nation's rocket propulsion needs. More than 500 scientists, engineers, technicians, and support staff are actively advancing rocket propulsion. Rocket systems such as Thor, Atlas, Minuteman, and Peacekeeper can trace their technological roots to test stands and facilities at the lab. The large F-1 Saturn rocket engines that propelled man to the moon were tested on the ridge overlooking the same dry lake bed at Edwards where the space shuttle landed after its early missions. In fact, the shuttle's main rocket engines evolved out of the lab's Air Force rocket propulsion technology. The large booster solid rocket motors and cases used on the space shuttle also evolved from early technology work and the development of segmented solid rocket systems at the lab. The era of the Strategic Defense Initiative Organization, known today as the Ballistic Missile Defense Organization, has advanced many areas of rocket propulsion technology. The lab was responsible for the development and the proof of concept of hover flights and suborbital test of interceptor vehicles. These vehicles can be space-based or utilized as theater defense systems. The recent test series of the Titan IV's solid rocket motor upgrade booster utilizes one of the lab's enormous static rocket test stands. The new booster will provide the nation with the capability of improving the Titan IV system's lift by 25%. The Phillips Laboratory Propulsion Directorate is setting the pace for tomorrow's rocket propulsion technology. The Propulsion Directorate is one of the founding members of a new program initiated to double American rocket propulsion capability across the spectrum of tactical missiles, spacecraft, and their boost and orbital transfer systems. The program, known as IPRIT, or Integrated High Payoff Rocket Propulsion Technology, blends the efforts of industry, universities, the United States Army, Air Force and Navy, and NASA. By the year 2010, IPRIT promises to give the United States such payoffs as increasing the payload capacity of expendable launch vehicles by 1/4 while reducing their launch cost by 1/3, increasing the payload capability of reusable launch vehicles 50% while reducing launch cost by 75%, increasing the repositioning capability of spacecraft 5 times, and increasing the payload of tactical missiles by 100%, or increasing the range 50%. In the area of boost and orbit transfer, the United States faces intense competition from Russia, China, Japan, and France. At the core of the Propulsion Directorate's efforts is the Integrated Powerhead Demonstration, otherwise known as IPD. The lab, in conjunction with contractors Aerojet, Rocketdyne, and Pratt & Whitney, is pioneering an engine demo featuring a mixed preburner stage combustion cycle, hydrostatic bearings and a booster-sized turbopump, and hot oxygen-compatible material. Of particular note is the hydrostatic bearing. Successful development of this hardware will cut the weight of reusable engines by 10% and expendable engines by 20%, enable an increase in turboshaft speed, and eliminate the bearing as the limiting performance and maintenance factor.
The stand that you see behind me and a component stand located nearby here are critical test facilities for testing our advanced oxygen, hydrogen, liquid rocket engines. The stand behind me is being ready to test engines for the Evolved Expendable Launch Vehicle for the U.S. Air Force, which we are supporting here at Edwards Air Force Base. The component stand nearby is our key facility for demonstrating the technology of an advanced oxygen, hydrogen, reusable engine for use on a military space plane. The Air Force is keenly interested right now in an airplane-like space plane that would travel from ground to orbit, conduct military operations, and return, and do that on a routine basis. We have the technology demonstrating today for a highly operable engine that will enable this space plane to function.
The Propulsion Directorate remains the national leader in solid rocket propulsion development. One of the key developmental areas underway involves process-efficient motor technology, which can best be described as an environmentally friendly way of building a rocket motor from the inside out. Rocket scientists have found a way to use corrugated polyvinyl alcohol, a vinyl sheeting known as PVA, and roll it within a shell. The final step in creating a rocket involves injecting an oxidizer into the shell, a step that can be completed long after the shell containing the PVA has been completed. This process creates a denser rocket motor for greater efficiency. It also means that the shells containing the PVA can be stored and transported safely and easily, since without the oxidizer, the shells aren't hazardous. Scientists in the High Energy Density Matter, or HEDM program, are working to develop fuels to increase the performance of rockets. Scientists are trying to find fuels that improve thrust efficiency, pack more propulsion energy into a small space, can be stabilized for long periods of time, and don't add weight, cost, and complexity. One aspect of this work involves cryogenic fuels, or fuels kept at very low temperatures. By using a popular propellant such as hydrogen in a frozen state, scientists can improve the storage life and stability of the substance while increasing the amount of fuel that can be stored.
The objective of the High Energy Density Matter program is to identify and develop high-energy chemical systems for use as advanced chemical propellants. Propellant is an obvious high-leverage place to look for systems-level performance improvements. For example, if you increase the energy content of a warhead by 20%, you deliver just that much more energy to your target. On the other hand, if you increase the propellant energy content by 20%, you can double the size of that warhead.
In order to satisfy the need for more efficient and long-lasting propulsion for spacecraft, the Propulsion Directorate is developing electric and solar propulsion systems. By taking a fuel and heating it through electric impulses, electric propulsions can provide low-thrust, high-efficiency thrusters in space for repositioning satellites. Current monopropellant thrusters for satellites restrict their ability to be repositioned over certain areas of the Earth during conflict, thus limiting the satellite's life. With so much dependent on our nation's ability to have the high ground of space, electric propulsion systems can move satellites to areas of the Earth where they're needed and still maintain a long life. In this way, fewer satellites are needed, which helps the nation maintain good use of its tax dollars. Electric propulsion systems can be made so as not to add weight to the satellite, an important consideration in putting payloads into space.
Electric propulsion is considered the most critical technology for increasing the capability of our geosynchronous communication satellites and for maintaining the United States' dominance in the international satellite community. Now, the reason for this is that the electric propulsion allows you to shrink the size of the overall propulsion mass, thus leaving more room for transponders on board the satellite. These transponders can now beam more signals back down to Earth and thus generate more revenue for the satellites.
A second form of efficient propulsion systems involves harnessing the sun's energy. The concept of solar propulsion is quite simple. Use the sun's rays to heat and expand a propellant to move payloads in space. Solar propulsion involves the use of reflectors to concentrate sunlight through a small aperture, then through a heat exchanger where the energy is used to heat hydrogen gas. The hydrogen gas then propels the rocket. This solar technology can be employed on an orbital transfer vehicle or to reposition satellites or other payloads already in orbit. There's also the potential of using solar technology to create a space tug that would dock with satellites in orbit and reposition them.
A solar thermal rocket propulsion system can take a payload of approximately 20,000 pounds from LEO, or low Earth orbit, to geosynchronous orbit where the communication satellites are in approximately 7 to 14 days at a cost savings of around $500,000 to $2 million, depending on the type of concentrator and thruster systems we use.
In the area of tactical missile propulsion, the Propulsion Directorate is exploring a number of innovative solid and hybrid propulsion technologies. The lab's newest effort is a joint Air Force and Japanese program to evaluate the benefit of using a high-energy liquid oxidizer in conjunction with a solid fuel.
Here at Phillips Laboratory, we're working a number of propulsion options for tactical missiles such as the one you see before me. One of our most exciting technologies is called hybrid propulsion. Rather than using existing solid propellants, we're using a new form of propellants where we use a liquid oxidizer and a solid fuel. By doing this, we can actually double the performance over existing technologies. We have a number of other benefits. For example, the missile becomes environmentally clean where we don't pollute. Another advantage is safety. By separating the fuel and oxidizer, we make the missile much less likely to burn or explode. And then last of all, we reduce the amount of visible smoke coming out in the exhaust of the missile. And this makes it much more difficult for the enemy pilots to see our missiles coming and avoid it.
0.
The Phillips Labs Propulsion Directorate is the nation's premier rocket propulsion laboratory. They have played a pioneering role in the development and evaluation of every rocket-propelled missile, launch vehicle, booster, and spacecraft in the Air Force inventory. And many of these rocket civilian counterparts use Propulsion Directorate technology. In the same way, the Propulsion Directorate has established the United States as the world leader in rocket technology. The lab promises to be at the cutting edge of technology in the 21st century. They have the right plan, the right facilities, and the right people.
The vehicle will reach maximum dynamic pressure at 58 seconds.